we're going to be switching gears. In essence, if you look in the book, we finished a chapter last time when we talked about the Jacobian. So you're probably going to feel very like, this doesn't seem to match with what we talked about last time. And what's happening is we're going to be starting a new part. And you could say that what we're going to be talking about is, you could call it vector calculus. And more or less our goal is to say, you know that fundamental theorem of calculus that you learned about way back in Calc 1? Here's a couple of cool things you can do with it. And we're going to see that in some different settings. Now, we're almost never going to use the words, and this is basically the fundamental theorem of calculus when we write stuff down. But we're going to point out to things and say, look, it's just like what we used to do. And so it's going to be an interesting couple of weeks. Now, we have to start somewhere. And so we're going to start that journey with line integrals. So let's talk about line integrals. In essence, we've done some really simple cases of integration, especially as far as it relates to line integrals. As we said, well, suppose I have a curve, y equals f of x. And I want to find the total. Now, I could think that's total area, but of course, when we think about integration, totals could be negative. I want to find the total beneath the curve. It's like, all right, we know what we're talking about. We know how to find it. We know the procedure. We're going to switch now and say, well, that's if I have this nice setting, y equals f of x. Suppose I do it in a slightly different setting. So now I have a curve down in the xy plane. So instead of having my part I integrate over, so here my part I'm integrating over just straight line, a to b. Now I'm integrating my part, it's actually a curved line underneath. It's at the bottom. It's following some path. And what's on top? Well, the height now depends where you're at on your curve. So the height, which is your z, it's a function of x and y. So I want to know what's the height of this surface, but only on the part that's over the curve. So our notation here is we're integrating over the curve c. So c here indicates there's a curve. The height, f of xy. And now we have this s. And we want to say, what's the total? Now, what is the s representing? Well, whenever we talk about d something, we think about it like a small change in. So, for instance, here, dx, we just think, our idea is to split our x into tiny little pieces. So, in other words, what we said is we come along and we said, split your inputs into little pieces, and for each part, say, well, what's the contribution of that part? So the dx was a measurement somehow of that small bit of change in your input. Well, it might not surprise you to learn we're going to do things the same way. So what's happening? Well, we have our curve, and what we're going to do is we're going to take our curve and we're going to break it into little tiny pieces. And for each little piece, I say, okay, what happens when I go up to the curve? And I say, what's that contribution? Well, then I have the small change down here. So what is the ds? Well, the ds is a bit of the length of the curve. So that's what the s stands for. So the s, again, that's the arc length. So we're going to say ds, a small infinitesimal change, but more commonly delta s, just to say, we've made a change in s. So, how do you find it? And the answer is, we already did. That was arc length. That was way back from a long, long time ago in the classroom right here. So we talked about arc length. And we said we used the distance formula. We can move it around. We can say that the change in the arc length is the square root of x prime squared plus y prime squared, and then change in t, so change in our input. And now it's like, aha, square roots. They're making a comeback. So we'll have to learn to deal with them. All right, so how do we do this? Well, so suppose we have our curve. It's parameterized by something. And so we have our x of t, y of t, t going from a to b. And I say if I want to integrate over my curve C, f of xy, oh, and there's a typo there, excuse me, that should be an s, I'll go fix that later. That is approximately the sum of saying, let's break it up into little tiny pieces, look and saying what's the value of the height on each piece times the width of each piece. Well, we know how to find the width. That's just the expression we had before. And the height, well, I'm really going to think of it as instead of splitting up the curve, I'm going to think about splitting up time. So again, I'm not splitting up the curve anymore. I'm splitting up the time between A and B and saying, well, how does that affect the curve? So that's what these t sub j are. So you start here maybe at t0, t1, t2, and so t is a time, which corresponds to a location once you use the parameterization. Well, that sum looks an awful lot like an integral because it basically is an integral, especially in the limit. And there you go. So how do you do a line integral? Well, the answer is we turn it into a nice integral of one variable. So we turn it into an integral that depends only on time t. So the integral from a to b of f of x of t, y of t, times the square root of x prime squared plus y prime squared dt. Now, one thing to note is if you look at the problem itself, so you have this curve in the xy plane. And you're asking about, okay, how much height is there over this curve? Now, the parameterization is a way to move along the curve. Does that change the amount of area that we're going to find? The answer is no. So it doesn't matter which parameterization we choose for our curve. The answer will still be the same. Now, given that our answer will be the same, you might say, okay, which one do you pick? In other words, which parameterization should you choose? And the answer is the one that's easy to work with. Because that's our goal. We want to be able to do things and have things that are easy to work with. Now, most of the time, we're going to have parameterizations. That's a hard word to say. They're going to be given to us. But if they're not given to us, we'll take a minute and think about, well, what's an easy way to write this? All right. Well, so now we have the definition. Time for some practice. So, find the integral along the curve of x squared y ds, where the curve, that's 3 cosine t, 3 sine t, where t goes between 0 and pi halves. Okay. Well, let's see. What do we have? So we have our integral along our curve, x squared y ds. That's going to be the integral from our a to b, so 0 to pi halves. And what's going to happen is everything's going to be rewritten in terms of t. So I have here something that says x squared y. Well, what do I do? Well, if you go up to c, you'll see there's a 3 cosine t, 3 sine t. So the 3 cosine t, that's the x. 3 sine t, that's the y. So everywhere I see the x, in goes 3 cosine t. Everywhere where I see a y, there goes 3 sine t. So we'll have 3 cosine t squared, 3 sine t, x squared y. Now the other thing is the ds. Well, maybe we should do that on the side here really quickly. So ds is going to be the square root of x prime squared plus y prime squared dt. So what is the derivative of 3 cosine t? Negative 3 sine t. So negative 3 sine t squared. Plus, what's the derivative of 3 sine t? 3 cosine t squared. Now, we hope, because there's not a lot of space here, that we have a nice expression, or this simplifies in a good way. Well, you get 9 sine squared plus 9 cosine squared. Now that's a nice thing. So what I really have on the inside is 9 sine squared plus cosine squared. And sine squared plus cosine squared is 1. So meaning that this simplifies to be 3 dt. So that's good. This was a case where the square root worked out nicely. Sometimes it does, sometimes it doesn't. All right, so we've done the hard part. As we said, let's take our line integral, which is over this curve. We've now expressed it as an integral over our parameterization, where everything now depends on our parameter t. Well, let's simplify. What do we get? We have 3 squared, which is 9, times another 3, times another 3. That's a lot of 3's. It's 81 of them. 81, integral 0 to pi halves, cosine squared t, sine t, dt. Now how would we actually integrate cosine squared times sine? Yeah, use substitution. What's the right substitution to make? U equals cosine. There might be others that work, but this is the cleanest one. Derivative of cosine? Negative sine. So what will end up happening here is we're going to get the following. We're going to get, I'll say 81. Then it'll be integral. Let's update our bounds. Cosine of 0, 1. Cosine pi halves, 0. That's a little strange, but that's okay. Cosine squared t becomes u squared. And the sine t dt becomes negative du. So the negative I can put out in front. Now, in fact, one thing I can do is if I don't like the negative, I can actually say, aha, I can use the negative to flip the bounds. Because oftentimes we're just so used to going from low number to high number. You don't have to. You'll still get the same answer. Now, do we know the integral of u squared? 1/3 u cubed. And we have a 81, which happens to have lots of 3. So we have plenty of 3's to spare. So 81 divided by 3 would be 27 u cubed from 0 to 1. Giving us a final answer of 27. All right. Good. Good. Now, this is a nice warm-up example. And this is a case where we have a curve that's in the plane. Now you might say, well, what if we're in 3 dimensions? Does it still work? And the answer is yes. You just have to sort of get a little bit more extra layer. So if I want to do a line integral in 3 dimensions, so I have a curve in 3-dimensional space, f of x, y, z ds. Well, that's the integral from a to b of f of x of t, y of t, z of t. So in other words, replace all of your parameters, or sorry, all your variables x, y, and z with what they correspond to as functions of t, and then it's the arc length. Now, a lot of this should look really familiar. In essence, if you covered up this f of x of t, y of t, z of t, it's exactly the arc length formula. So what you're doing is basically you're saying, I'm going to attach a value to every point along the curve. And now I'm going to see, well, what's the total? One way to think about this that's kind of intuitive, and we'll see this in just a moment, is to say, well, let's think about our values being like a density. And so now we're saying, what's the total? So here's an example in 3 dimensions. Find the integral along the curve of the function z plus x ds, where the curve is cosine t, sine t, and t. Now, do we know what this curve looks like? Cosine t, sine t, t. Well, suppose I just said cosine t, sine t. Do we know what that looks like? It's a circle. In fact, that's how circles are done in trigonometry. You think of the x-coordinate as the cosine, the y-coordinate is the sine. So when you see cosine t, sine t, you're like, ooh, circle. Okay. So that's circle, which means if I didn't see the z part, now how could I not see the z part? Look straight down the z-axis. So if I was looking straight down the z-axis, what would happen is I'd see the following. I'd see the xy plane, and I'd say, oh, you're just going around in a circle. Now, again, that's if I look straight down the z-axis. So now I put my perspective back. I say, okay, what my curve is going to do is it's going to circle around the z-axis. The z-axis is the origin, if I'm looking straight down. So I'm going to circle around the z-axis, but I also do something, which says, as I circle, I increase my height. So what's happening is I start at height 0, and I circle around, but then I drift up. So what's the net effect? So I'm going to start here, which would be at the point 1, 0, 0. That's at time 0. And then I'm going to circle around, and I'm going to be moving up until I end up there at time 2 pi. And so what this curve is it's part of a helix, where you make one loop around. So that's what the curve is. Do you need to know that to answer the question? No. But it's fun to know. It's good to know things. It's good to know things. All right. Well, what do we need to answer the question? Well, we need to know a couple of things. We need to know the time we're going between. So I need to know 0 and 2 pi. Those give me my bounds. That's what I need to know. I need to know the parameterization, because I have that these will give me what my variables become. X will become cosine of t. Y will become sine of t. Z will become t. And so those are things I need to know. So we'll get the integral. My bounds are 0 to 2 pi. Z plus x will become t plus cosine of t. And then the ds. Well, the ds, that's this piece here. That's the part that corresponded to arc length. And so we're going to go through and work that out. Well, let's see what that becomes. Hopefully there's enough space there. Okay, so we'll have the square root of, what's x prime? Negative sine. What's y prime? Cosine. Of course, we're squaring that. And what's z prime? 1. Okay, what does this become? Square root of 2. So that means that this part, once I attach the dt onto it, that ds will become square root of 2 dt. So in some sense, both these examples have actually been circles. If you go back to this problem, you'll see it's actually part of a circle. Circles are very convenient, but they're not the only thing that happens. So now we're pretty close. The square root of 2 is a constant, so I can just pull that to the side. What's the integral of t plus cosine t? Sorry, what? Right, 1/2 t squared plus sine of t. And evaluate from t equals 0 to t equals 2 pi. Well, we're going to have 1/2 times 2 pi quantity squared. So that would be 4 pi squared times 1/2. We can write that as 2 pi squared. What's sine of 2 pi? 0. Okay. Plug in 0. 1/2 times 0 squared? 0. Sine of 0? 0. So that's it. There's our answer. And we're done. Oh, these aren't so bad. It just says everywhere where you see, your x, your y, z, replace it by the appropriate function. It's by the parameterization. And don't forget the ds term. So yeah, okay, good. These we can do. These we can do. All right. Well, what else can we do? Another thing we can do is we can say, let's take a parameterized curve and we can think of it as basically modeling a wire. So I have this wire and I can say, how do I find the wire? Well, it's what you see if you move along the curve. So in essence, the wire would be the path left behind of a particle moving along the curve. And what can we do? Well, maybe we have a wire that doesn't have a uniform thickness. So maybe some parts are more thick, other parts are less thick. so that the density of the wire changes. And you might say, well, what's the mass? And so that's what the question here is. You have a wire bent to form the top half of a circle of radius 2. And it has the property that the density varies. So it's not uniform density. And our goal is find the center of mass. Okay, so we're going to sketch the picture here. And, all right, half circle of radius 2. So our wire is going to look something like that. So there's -2, and there's 2. And our goal is to find the center of mass. Now, if we were to try to draw this more accurately, we could say, well, the further up we go, the more dense we get. So it's much more dense at the top, and then less dense as we get back down. So we should expect that we should be somewhat biased towards the top. But we'll find out later on. Okay, so how do you find mass? You integrate density. See, that nice thing is if you just say, what's mass? It's the integral of density. Then you're like, okay, I can apply that in any setting. So we can apply it in our setting right now. So we can say that the integral of density is our mass. So we're going to integrate along our curve C. So here's our curve C, this half circle, density ds. Now, what don't we have? We don't have what C is, because it wasn't given to us. So we actually get to pick. So, but we do have delta. That's the density. That's given to us. All right, so we're integrating y. Well, so it's a half circle. What are some things that we can use for a half circle? What's the parameterization? Cosine and sine work great. So we could do C equals, what would be the x coordinate? Cosine? What would be the y coordinate? Sine? Is that, do we need to change anything? I can't help but notice there's some suspicious gaps here. Yeah, so cosine and sine is a unit circle, radius 1. We need radius 2. Very conveniently, we have some space. Now, we're not quite done with the parameterization. There's something else we need to know. What is it we need to know? Where t goes from. Yes, good. So where does t go from? 0 to pi. Now, we could use that, or if you were more bold, we could say, I don't have to do trig. Look, this curve is the x squared plus y squared equals 4. So I could rewrite this as y is the square root of 4 minus x squared. Okay, that's absolutely true. That is the curve we want. And here's another parameterization that we could say. Well, y will be the square root of 4 minus t squared, and x will be t. Because notice if we let t equal x, then you get square root of 4 minus x squared. And then we could have our t go from -2 to +2. Now, both will give us the same answer, but I strongly suspect one will be easier to work with. Which one should we work with? Let's work with the cosine sine. For fun, on your own time, outside of class, you can try the other one and see what happens. Okay, so let's find our mass. So, we should probably say, what's our ds become? So if we use the first one, ds, well, that's the square root of, take the derivative with respect to x. So we've done a couple of these, so I'll do that a little bit quickly. -2 sine squared, plus derivative with respect to y, that's 2 cosine squared. And if you simplify that, it becomes 2. So we get the integral. Our time goes from 0 to pi. And y will be 2 sine of t. and ds will be 2 dt. So we get the integral of 4 sine of t. What is the integral of 4 sine t? Negative 4 cosine t. Evaluate from 0 to pi becomes cosine of pi, negative 1. So negative 4 times negative 1, positive 4. I'm going to subtract cosine of 0 is 1, so it'll be 1 times negative 4. So I'm going to subtract negative 4. But of course, subtracting negative 4 is the same as adding 4, so we get that our mass of our wire is 8. And you might wonder, 8 what? Well, whatever units we were going to use, but forgot to mention in the problem statement. Okay, so are we done? No, we're not done yet. What do we need to do next? We got to take a moment. Which moment do we need? Well, we need mx and my, right? Because we need to find the center of mass. Can we save ourselves any work? Yes. Okay, well, how can we save ourselves work? Well, we can save ourselves work by seeing their symmetry. So in other words, if you flip it across the y-axis, you're going to get the same shape, same density, which means wherever your center of mass is, it has to be on the y-axis. Well, that tells us that x bar is going to be 0. Okay, so we don't need to do the integral that's going to lead to x bar. We need to do the integral that's going to lead to y bar. So that means we're going to do m sub x. Yes, of course. You know, because it's that really, got to remember it has that weird thing there. So that's x there stands for distance to x-axis, which is y. So this is the distance to the x-axis, but then you get another y because you have the density. Distance times density, ds. Well, all right. So integral 0 to 2 pi, y squared. Well, that would be 4 sine squared. ds hasn't changed. It's still 2 dt. Is what just pi? Oh, my bounds. Yes, thank you. Thank you. It is just pi, 0 to pi. All right. 4 sine squared of t. Well, times another 2, so that's 8 sine squared of t. How do you integrate sine squared of t? 1 minus cosine 2t over 2. Power reduction. All right. Well, the 8 times a half is the 4. All right. Integral of 1 t minus integral of cosine 2t. 1/2 sine of 2t. And then I'm going to evaluate from 0 to pi. And if we plug this in, plug in pi, well, we get 4 times pi, then minus 1/2 times sine of 2 pi. That's 0. And then plug in 0. We get 0. So we end up with 4 pi. All right. Now, is that our answer? No, but we're getting close. All right. Really close. Really close. Finally, we get to the point, y bar, you take the moment, m sub x, divide by the mass, and you end up with pi halves, which would mean that our center of mass is at 0, comma, pi halves. Now, is pi halves reasonable? Yes. Okay, I like that. Yes. All right. Good. Well, what is a pi halves about? Like, really bad estimate. 1.5, probably 1.57, something. So between 0 to 2, because that's at 2, that says I'm a little over 3/4 of the way. So the nice thing is that makes sense, because we said there's more mass near the top. We should be biased towards being near the top. And we definitely should be somewhere between 0 and 2. Now, this is a case where the center of mass is actually not part of the wire. It's outside of the wire, but that's okay. Center of mass doesn't have to be a part of your object. Now, if we had gone an answer above 2, or an answer that was negative, we would have been concerned. But this is a reasonable answer, and we're going to stick to it. We should have done this one. Would have been fun. Would have been fun. Maybe if we have time at the end of class today, we'll try that. All right, but there's still a little bit of work to do. Let's talk about work. Now, if you go back, boy, there's so many things we learned at the beginning of the semester that we get to recall now. One of the things that we saw about work is we saw that we could do work by doing force times distance. Now, that's the basic expression. But then we said, well, we can clarify it a little bit, because we might have a force vector, which says I have an amount of force going in a certain direction. And then instead of thinking distance, because we like to use the same letters in our equations, we said displacement. So displacement is another vector which says, okay, what was the result? How much did you move? And so you had to have a direction and an amount moved. And then if you take the dot product of those two, that was the work. Okay, so work is found by taking the force, dot it with the displacement, and we're good to go. However, that's a very simplistic thing. It says your force is always acting in the same consistent manner. Your displacement is always in the same consistent way. What if we did something more complicated? Now, what do I mean by something more complicated? The basic setup you should have in your mind is I have a curve that's in the plane. So maybe you should think of it as I have this track. And on this, I have to move perhaps some object. So here's a little bit of object that I'm moving along here. And as I move the object along, things happen. First off, I'm not always going to have my displacement being in the same consistent direction, because the track I'm on is curved. But it also might be the case that the force I have, it's varying with my location. So now my force and my displacement are changing based on where I'm at. So what do? How do I find the total? Well, putting on our calculus hats, what do we do? What's our approach? What? Well, our approach is to say, I'm not going to find work as one thing. I'm going to find it as lots of little things. In other words, take up the amount of work you're going to do, split it into little tiny parts, and say, what's happening with each one of those parts? And if I can know what's happening with each part, and then I put them all together, that's the total work. Okay, so how do we do it? Well, we say our work is adding up, and that's our little pieces, adding up for each little piece, what's the force at that moment, and then what's the displacement? So this is the part where you have to think a little bit. How do you find the displacement? I'm moving along the curve. So the direction of the curve, that's given by the direction from the curve. That's the tangent vector. The tangent vector gives me the direction. Now, a vector has two things. Every vector has two things, a direction and a length. So the t, that's the unit tangent vector, is a direction. The delta s, that's the amount I move in that direction. So if I put those together, that gives me how much I've total displacement, my change. So if you look at it, you say, okay, a sum is just a fancy integral. I mean, this goes to an integral. So I'm integrating along the curve, f dot t delta s. So f dot t ds. And the way you should read this is to say the following. It's like, all right, f dot t ds is the amount of work over a little tiny piece, then I'm adding it up. Now, we do know what the unit tangent vector is, and we also know what the displacement is. So let's parameterize our curve, x of t, y of t. And if we do that, then the unit tangent vector is found by taking the derivative, divide out by the magnitude of the derivative. R prime of t over the magnitude of r prime of t. So that's not so surprising. We saw this before when we talked about motion. The ds is the exact same thing we've been talking about. It's that arc length. And you're probably thinking, oh my goodness, we're having even more square roots come into this. How bad is it going to get? But the answer is, it's not going to get worse. It's about to get better. What happens? Look at it. If I multiply the t and the ds together, what do you see? Cancellation. That's the good stuff. That's the really good stuff. So, when you multiply t times ds, what you end up with is x prime of t, y prime of t. The square roots are gone. And so, and then of course we do have a dt on the end. So sometimes we write this as dr, which is a little bit of movement along the curve. And you can also say, well, put the dt inside. So x prime of t dt and y prime of t dt. And you can say, well, the first one, that's like our change in x. X prime of t, rate of change of x with respect to t, and dt is the amount of change of t. So this would be the amount of change of x. Similarly for dy. So, now what happens? Well, if I have a vector valued function, f, I'll write it as m comma n, then we have lots of different ways to express the same thing. And you might say, well, which way do I need to know? And the answer is, you should know that they're all the same. And then you should use the one that's easiest to work with. We have put all variations of these expressions on exams in the past. This is the one that we'll almost always will work with. But you should just know that they represent the same thing. You're basically finding something like a work. This one is kind of the fun expression right here. Because if you look at it, what did we do? Well, we took f, which is the vector mn, and we dotted it with dx dy. So you'd have m dx plus n dy. Now, one of the things that we haven't said yet today, and it really is useful to point out, is that when you look at these integrals, they do look like they're multivariable integrals. In other words, I see this expression, I see both an x and a y, and I'm like, oh, this is a multivariable integration problem. I have to do like a double integral or maybe a triple integral if I'm in 3 dimensions. And the answer is no. These are really, truly single variable integrals. Because what's going to happen is that everything is going to reduce down to the parameterization. So whatever t is, that reduces down to that function. It's a function of one variable. One of the things you should watch for is just count the number of integral signs. When you see a single integral sign, it's a one-dimensional type object. So it's a curve. Later on, we're going to talk about two-dimensional type objects. So you'll see 2 integral signs. And if you ever do a 3-dimensional type object, well, 3. Okay, you probably saw that one coming. All right. That's not so hard to figure it out. Some other things to note here. The same arguments work in higher dimensions. So it doesn't matter whether you're in 2D or 3D, you can still do line integrals. And so we'll do examples of line integrals in various settings. One other important thing, and this is the very bottom note here, the integral depends on orientation. Now, what does that mean? Well, it means that if you reverse the direction along your curve, you're going to get a different answer. So, if I have my curve, and I'm going between 2 points, it matters whether, let's call this point A, call this point B. It matters whether I'm going from A to B or I'm going from B to A. Because I'm going to flip. And the result is, whenever we talk about orientation, we're really talking about a sign. So orientation is just a fancy way for saying you're going to change the sign of the answer. The reason it happens is you look at the tangent. If I'm moving from A to B, at that point, I'm moving in the forward with respect to x direction. If I'm moving from B to A, I would move in the opposite direction. And because these expressions involve t, that's why it depends on orientation. Now you might say, doesn't it always depend on orientation? If you actually go back to the original setup, which we talked about at the very beginning of class today, which was thinking about of how much area there is above this curve, that's independent of orientation. So there is some subtlety, there is some interesting thing going on here. And once you introduce orientation, things get a lot more interesting. All right, let's do some examples. So we're going to do one of these problems. Let's find the integral along the curve of xy squared dx plus xy squared dy for the curve C going from 0, 0 to 2, 2 as shown below. And so here is our curve C conveniently given to us. Here is the point 2, 2, and over here is the point 0, 0. All right. Well, how do we go about doing such a thing? Well, we need a parameterization. Now, one thing you can do is you can say, let's split this into two parts. Say a part 1 and a part 2. So a part 1 is just going to be directly moving across horizontally. All right. Well, if I'm moving in a nice horizontal fashion, let's talk about our x component and let's talk about our y component. What's true? Let's do the easy one. What can you say about y here? Y is 0, because I'm always on the y equals 0 line. Now, what can you say about x? Our x changes and it goes from 0 to 2. So what we can do for our parameterization is we can say, well, we need something to indicate varying. It's changing. So we'll throw our parameter in. And then we'll just say that it goes between 0 and 2. And so this is if you look at it, when I start at time 0, I'm at 0, 0. And at time 2, I'm at 2, 0. It's exactly the parameterization that we need. All right, so if we do this integral here for this curve, so I'm integrating along curve 1 of my expression xy squared dx plus xy squared dy. What do I do? Well, I use the time for the bound, 0 to 2. Everywhere where I see an x, what do? I put a t. Everywhere I see a y, I put 0. So this becomes t times 0 squared. What will dx become? Well, dx, you take the derivative of the x. Derivative of x? Derivative of the t would be 1, or you could say dt. X would be t again. 0 squared. Derivative of y? 0. Well, I think this is an integral we can probably do. What does it become? It becomes the integral of 0, which is 0. Okay. Woohoo! Our favorite kind of integral. The one we don't have to do. All right. Well, that was one of them. There's a second part to it, though. Let's talk about this second leg of our journey. What's true about points from the corner where we turn to the top? X is always 2. So we're just going to say that parameterization, we have x will be 2. What happens with y? It goes from 0 to 2. It varies. So we can throw in a variable name for it. We'll just call it t. And here, t goes between 0 and 2. Now you might say, wait a second, we already used time between 0 and 2. But it's okay because we're breaking this into two parts. And for each part, we can use whichever parameterization is easy. So that's why let's use the easy stuff. We'll be all right. Okay, so for this one, well, let's see, can we fit it here? Maybe. We're going to do the integral xy squared dx plus xy squared dy. So, integral 0 to 2, what do you get? Well, x will be 2, y squared, t squared, dx, 0. Well, that's not promising. X will be, again, 2, y will be t squared, and dy will be dt. Ah, woohoo! We actually get to do something this time. All right, what's the integral of 2t squared? 2/3 t cubed. Evaluate from 0 to 2. We plug that in, we get 16 over 3. 2 cubed is 8. 8 times 2/3 is 16/3. Plug in 0, you get 0. Now, what does that say? Well, it says that the contribution from the first part of our journey is 0. Contribution from the second part is 16/3. So our total is 16/3. Put them together. Now, that's if we went and made a turn. Suppose we didn't make a turn. Suppose we said, I don't want that particular curve C. I want to go directly from point A to point B. Do not pass go. Do not collect $200. What do we do? Well, what do we need? We need to find a parameterization for this curve. So, is there a nice parameterization? T comma T. And where does T go from? 0 to 2. All right, so let's see what we get. We're going to get the integral along our curve of xy squared dx plus xy squared dy is going to be the integral from 0 to 2, because those are my bounds for time. X times y squared will become t cubed dx dt. Yeah. I'll put 1 here. 1 times dt. I'm going to just factor out the dt at the end. Okay, and this xy squared dy, what will that become? T cubed again. And dy is still 1 of y. So again, every part of this expression, to figure it out, go and figure out what's the x, what's the y. If I want to find dx, look at x prime. If I want to find dy, look at y prime. So we're almost there. We're almost there. Okay, so t cubed plus t cubed is 2t cubed. What's the integral of 2t cubed? 1/2 t to the 4th. And we're going to go from 0 to 2. We plug it in. Well, t to the 4th, 16 times 1/2, 8. And that's just one piece. Now, you might notice something, that 16/3 and 8 are not the same. Now, you might say, I'm neither surprised nor unsurprised. It's okay. What should my feeling be? Well, in some sense, you might say, it kind of would have been nice if they were the same, because maybe there's some nice relationship that comes out. This shows you it's not always going to be the case. But maybe, just maybe, if we're in the right setting, where we can do something like fundamental theorem of calculus, it won't matter. And that is what we're going to build up to. So let's do a little bit more. Now, earlier we said, hey, we can do this problem about a wire in the center of mass, and we used a parameterization that used cosine and sine. And I said, look, you could use the parameterization for the circle. Well, but maybe we shouldn't, because it takes some time. Well, we have time, so let's do it. So we're going to cover this up, and let's find out what happens, and hopefully we get the same answer. Now, one of the things we should probably do to start is take a moment to figure out what is our ds. So ds is going to be the square root of x prime squared plus y prime squared dt, which in our case is going to be the square root of, well, x prime is 1. 1 squared plus y prime. That's a little bit more interesting. 1/2 4 minus t squared to the minus 1/2. Then we're going to multiply the inside by minus 2t. Chain rule. Now all that squared, dt. So this becomes the square root of, what happens here? Well, notice the 2's cancel. So we get 1 plus, when we square, the minus goes away. You're going to get t squared over, and here, is going to be 4 minus t squared, but downstairs because of that negative 1/2. Now if you add those terms together, you'll see something nice happens, because this 1 is really 4 minus t squared over 4 minus t squared. You add the numerators, the 4's cancel, so you end up with ds is 2 over square root 4 minus t squared dt. Okay, so there's our ds. We'll use that for our computations. Now, which computations? We have two things we need to compute. We need to compute the mass, and we need to compute the moment. So let's do the mass. That's the integral from -2 to +2 of our density. Well, let's actually put it what it is. It's the integral along the curve of our density, which is y ds. So when we put it into parameterizations, -2 to +2, what's our density? Our density is y, which becomes square root 4 minus t squared times ds, which is 2 over square root 4 minus t squared dt. Now you might notice something nice. The square roots cancel. So this becomes, well, 2t, evaluated from -2 to +2, which is 4, subtract -4, or 8. All right, well, that wasn't so bad. Okay, what about our other computation, our moment with respect to the x-axis? Well, that'll become the integral -2 to 2. Now remember, what is this going to do? It's the integral along the curve of the distance to the x-axis, which is y, times y ds. All right, well, that means I'm integrating y squared. So that will be square root of 4 minus t squared squared times 2 over square root 4 minus t squared dt. Now we can cancel one of these off, but then we're left with the challenge. How do you integrate from -2 to 2 of the square root of 4 minus t squared dt? Well, I mean, one thing you could do is trig substitution, lots of work, hope you don't make a mistake. Or a better thing is to say, I can interpret this integral. Now, don't worry about where it came from, worry about what is it right now. And the answer is, what it is right now is you're going to go from -2 to 2, and we can interpret it as being an area. So it's this area. So what that means is it's half the area of the circle of radius 2. So this will become 2 times half of the area of a circle of radius 2, which is pi r squared. And that becomes 4 pi. So we're now ready to put our answer together. We say, look, we have the moment, we have the mass, we still have that x bar equals 0, and now we can conclude that y bar, which is our moment with respect to x, over our mass, so that's 4 pi over 8, which is pi over 2. And so our center of mass will be x bar, y bar is equal to 0 pi halves. All right. Now, is it the same? Hopefully. Let's check. It is. It is. And one of the things we should point out, we've mentioned this, is notice that one of our parameterizations, namely this first parameterization, traveled the curve this way. Because you start at 0 here, you end at pi there. The other parameterization traveled the curve the opposite way. But we still got the same answer. In other words, it didn't matter which direction we traveled, because this is a line integral where orientation doesn't matter. Of course, there are other line integrals where orientation does matter. And for those integrals, we'll talk about more in the next few days. But for now, we're going to focus on really line integrals where orientation doesn't matter, because we're going to do a few more examples. some of our favorite problems, word problems. We love a good word problem. All right. As champion of the reality show, the Ultimate Extreme Roller Coaster Happy Fun Hour, you have recently been hired to help design a new ride. Currently, you're working on a portion of the ride where the cart will move along the curve 5 plus a half t squared, 2 plus 4t times square root of 2t to the 7/4, and 2/3 t to the 3/2, where 0 is less than or equal to t less than or equal to 1. You need to determine the amount of material needed to build the supporting structure for the ride, which will depend on the distance to the ground. And the ground is the xy plane, which means our distance is z. All right, so help estimate the amount of material needed by finding the integral along this curve of z ds. So what's happening? Well, let's see if we can draw a picture. Probably won't be a great picture. All right, so here's our ground, and what's happening is there's some sort of roller coaster ride coming along doing something. All right, now this roller coaster ride is sitting on top of some curve here down in the plane. And what we're wanting to do is we're wanting to say, all right, how much support structure do you need? Well, you need to make sure you have stuff that can support the ride. So you have to build supports going up to the ride. And so that information is found by what's the area from the height down to the bottom, because then you can say, okay, here's how much support structure I need. All right, now when you look at this, you're probably like, that's a lot of words. But when we think about it, what do we need? Well, it tells us that's what we need to find. It also says, here's the curve, and there's our time. And we can ignore everything else. That's it. So it says, find this integral along that curve. Here's the curve. There's our time. See, one of the things about word problems is you have to sort of extrapolate. What's the important information? In this case, we can just quickly grab the key pieces. All right. So let's work for a second. Let's do our ds. So ds is going to be the square root of x prime squared plus y prime squared plus z prime squared dt, which is going to be square root of, take the derivative of x prime with respect to t. The 5 goes away. Derivative of a half t squared is going to be t. So t squared. The next entry, the 2 goes away, and then derivative of 4/7 square root of t, t to the 7/4. Well, the 2 gone, 7/4 comes down, 4/7 and 7/4 exactly cancel. Suspicious that it works out so nicely. So what's left? Well, what's left is the square root of 2, and then it'll be t to 1 less power, 3/4. That's going to be squared. Come to our last entry. Again, we have the 2/3, but the 3/2 comes down. All right, that's going to give us 1. And then we're going to have t to the 1/2 left. So plus t to the 1/2 squared dt. Now, that is the square root of t squared plus 2 t to the 3/2 plus t dt. Now, when we're looking at problems like this, sort of our initial reaction is to say, well, what are we looking for? We're looking for ways to deal with square roots. And there's a couple of ways to deal with square roots. But one thing is we should look for things which factor nicely. In other words, we should suspect squares floating around. Now, let's see what we have in our case. All right, we have a t squared, 2 t to the 3/2, and t. The coefficients here are very suggestive. See the coefficients? 1, 2, 1. That's the kind of coefficients you see when you talk about a plus b squared. Now, one thing to help us see what's happening is we can factor t out. T times, then I'll have a t plus 2t to the 1/2 plus 1. All right. Well, that 1 is good. T to the 1/2. How do I think of t now? Well, I can think of it as t to the 1/2 squared. And then I say, now that's good. Because this becomes the square root of t times t to the 1/2 plus 1 squared dt. So we're almost there. Square root of t is t to the 1/2 times t to the 1/2 plus 1. So if you clean it up, you're going to end up with t plus t to the 1/2 dt. All right. Well, that's great. That means our ds is very clean, very simple. Now we're ready to talk about the integral along the curve. Okay, well, so the integral along the curve of z ds is going to be the integral, the bounds, 0 to 1. The z is the 2/3 t to the 3/2. So 2/3 t to the 3/2. And then our ds, that's, there it is, right there, times t plus t to the 1/2 dt. So this is the integral from 0 to 1. We'll multiply this through. We get 2/3 t to the 5/2, because I'll have 3/2 times plus 1, plus 2/3 t to the 4/2, or simply t squared. We integrate. So we're going to get 2/3. Now, it'll be 7/2, because I add 1 to the exponent. And 7/2, what I'll do is I'll multiply by 2/7. So t to the 7/2 plus another 2/3 times t squared will be 1/3 and t cubed. And evaluate from 0 to 1. Now when we plug in 0, we're going to get 0, so that's good. We plug in 1, we get our coefficients. So first coefficient, 4/21, plus second coefficient is 2/9. Now let's clean it up. Let's make it a single fraction. Well, what divides, not divides both, but what number is divisible by 21 and by 9? Well, really, this is 3 times 7, and this is 3 times 3. So it's 3 times 7 times 3, which is 63. So this we can write as 12/63 plus 14, because I multiply by 7 here, over 63. 12 plus 14 gives us 26/63. And we're done. So, now you might say, what does that number mean? Well, in essence, what that number represents is the amount of area down to below. So, in some sense, you could say that's the amount of scaffolding, proportional at least. So, that's how we can use that number. Okay, well that was good. That's a nice problem. Let's do another problem. All right. So, while separated from your vertically challenged traveling companions, you find yourself lost in an underground network of caves. While fumbling around in the dark, you come across a ring. While you cannot see it clearly, you can tell that it has an unusual property. Namely, the density is not perfectly symmetric around the center. Upon further reflection and weighing it in your hand, you realize that if you model the ring by a unit circle centered at the origin, the density of a point on the ring is given by x plus y plus 2. This throws the center of mass slightly off from the center and thus is a most unusual ring. Subsequent experimentation will reveal that it has even more interesting properties than its density. Now, use this information to find the center of mass of the ring. All right, well, what do we do? Well, let's try to figure out what we need to do. Now, the last sentence always gives sort of away what's happening. This is a center of mass problem. All right, well, what kind of a center of mass? The ring, we're told, is a unit circle. Now, the ring, if you've ever seen a ring, it's the outer edge. So, this is another wire problem. So we're working on a wire. The wire is a circle. And, all right, so now we know it's a type of problem, center of mass. We know the region is the unit circle. And the last thing you need to know for mass is density. So these are the three key things that this problem will tell us. And once we solve this, well, we'll know about the ring. That one ring that will rule them all, one ring that will find them, and one ring that will bring them all, and in the light of calculus, bind them. All right, so let's get going. Okay, so here we go. Let's draw a picture to get us started. So we come here and we draw a unit circle. So there's our ring. Now unit circle just means radius 1. Now our density is x plus y plus 2. So the question is, does this ring have symmetry? In other words, is there some line where I'm going to be the same? Now, where is the ring dense? Well, it's very dense where x plus y is very large. So if I want both x and y to be very large, I want to head in this direction, which means it's very dense over here. Where is it very undense? One might say thin or sparse. Well, when x plus y is very small, or if you like, large in a negative sense. So it's very sparse in this direction, so on the other side. So if you were to sort of get a feeling for density, you would see that it's dense, but then it's getting less dense. All right. So now the question is, does it have symmetry? Where's the right symmetry? It's not with respect to the x-axis, and it's not with respect to the y-axis. So your symmetry doesn't always have to be with respect to some axis. In our case, our symmetry is here. This is a line of symmetry. And what is this? Well, this is the line y equals x. And what happens if you flip across the line y equals x, you flip the roles of x and y. So here you can see if I change the roles of x and y, I haven't changed the density. So that tells us that we have our line of symmetry is y equal x. Now what does that say about our center of mass? Well, we can conclude that since I'm on the line of symmetry, it must be the case that y bar is x bar, which means I only have to compute one of the two. Because once I have one, the other is a freebie. All right. Well, still have to compute one. So let's think about what we'll do. Okay, so we want to have a parameterization. We'll go to the classic parameterization of the unit circle, which is cosine, sine. And I say classic because, again, that's what trig is based off of, where you say the x-coordinate in the unit circle, that's the cosine, and the y-coordinate is the sine. Time will run between 0 and 2 pi. So what happens? Well, let's do a quick computation for our ds. ds is going to be the square root of derivative of cosine, negative sine, squared, plus derivative of sine, which is cosine, squared, dt, and you get sine squared plus cosine squared, which is 1, meaning ds is dt, which is a very convenient thing for us to work with. So we're ready to do our computations. First off, mass. Mass is the integral along the curve of density. So that becomes the integral from 0 to 2 pi of density, which is x plus y plus 2. So I'm going to have x plus y plus 2. All right. Well, we can integrate this. The integral of cosine is sine. Integral of sine, negative cosine. Integral of 2, 2t. Evaluate from 0 to 2 pi. Well, sine of 2 pi is 0. Minus cosine of 2 pi is minus 1. Plus 2 times 2 pi is 4 pi. And, okay, then we're going to subtract sine of 0, 0. Cosine of 0 is minus 1. And 2 times 0 is 0. Well, the minus 1's cancel, so we end up with 4 pi. So there's our mass. Good. Now that's not enough for us to find the center of mass, but we definitely need that information to make progress. Now the next thing we need is the moment. Now the question becomes, which one? Well, the answer is it won't matter, because whatever moment we find, we're going to find either x bar or y bar, and so we just pick whichever one we want. Since we've done a moment with respect to x, let's do a moment with respect to y. So this will be the integral along the curve of x times density ds. So this becomes the integral of 0 to 2 pi. So this x is going to become cosine. So what's going to happen here is it's going to be the same thing except there's an extra cosine. So it's going to be cosine times cosine, which I'll write as cosine squared, plus cosine times sine, plus 2 times cosine. And that would be dt. Whoops, there's a mistake here. That should be dt, not ds. All right, well, we fix it. Okay, always good to fix our mistakes. Cosine squared. To integrate cosine squared, we use power reduction. So this is 1/2 plus 1/2 cosine 2t. Okay, so we're ready to integrate now. So what do we get? Well, we're going to get 1/2 t plus 1/4 sine of 2t. All right, that's the first part. How do we integrate sine times cosine? Well, probably the easiest thing for us to do is if we say sine is u, then cosine would be du. So I see a u du. So the integral of that is going to be 1/2 u squared. And then we have the 2 cosine. The integral of 2 cosine is 2 sine. And we're going to evaluate all this from 0 to 2 pi. Oops, almost out of room. All right. So 1/2 times 2 pi gives us pi. Sine of 4 pi, 0. Sine of 2 pi, 0. Sine of 2 pi, 0. Then we have 0. Sine of 0, 0. Plus another 0, plus another 0. Ah, so it's pi. Okay, so what do we know? Well, we know that y bar equals x bar, because we said that before. And we know that x bar is the moment with respect to the y-axis over the mass, which is pi, over 4 pi, which means no more pi's. Pi's are gone. Or 1/4. So our center of mass should be 1/4, 1/4. Now, as always, does this make sense? Well, if we have a ring, one thing should be true. The center of mass should be inside the ring. So that's definitely 1/4, 1/4. If we mark it somewhere right around here. The other thing, of course, is not only should we be in the center, in the middle of the ring somewhere, but we should be biased towards where it's most thick. And that's definitely happening here. So this is a good answer, a reasonable answer, and we did the math, so we're going to go. That's it. That's the answer. Okay, well, let's see. I think we have one more. So, last one. After a heavy snowstorm, you decide to build a small fort in preparation for a snowball fight with some friends. Now the fort consists of a curved wall built out of snow to offer something to hide behind. The wall you build will lie on top of the curved C with x of t, y of t is 3t squared, comma, 2√3t cubed. Well, that's probably important. In fact, I should probably circle that. So we have a curve C. And for 0 less than equal to t less than equal to 1, that gives us times. And the distances are measured in feet. The height of the wall at a given xy is 1/2 x plus 5/2 feet. Okay, so this is the height. Now, you'll need 1 cubic foot of snow for each square foot of surface area of the wall. Use a line integral to determine how many cubic feet of snow you will need to build this wall. All right, so what's going on here? Well, let's see if we can draw a sketch. We have our ground here, and what's going to happen is we're going to build a fort. It's really just sort of a wall, a little enclosure, and so we can then say, all right, we're going to be building this fort out of snow. And now what's the purpose of this fort? Well, you can imagine that if you're in a snowball fight, you could just sort of duck and look out from behind your fort. So that's what our purpose is. Now, what do we want? Well, if we can find the area of this, so in other words, you can think of this as almost like, maybe it's like drapes you're hanging down. So if we can find the area, that will tell us how much snow we need. Because if you look, what does it say? You will need 1 cubic foot of snow for each square foot of the surface area of the wall. So that tells us that there's a translation between the amount of snow we need and how much surface area there is of the wall. So really this question says, how many cubic feet of snow do you need? It's really a question about what's the surface area. In other words, what's this area here? That's what we need to figure out. Okay, well, how do we do it? Well, it tells us use a line integral. All right, well, what line integral? Well, we need to know the following. We have to know this curve, that's the bottom of our pyramid. Well, sorry, not our pyramid, our fort, our wall. That curve is here. So we're going to take the integral along the curve of what? Well, the height. So 1/2 x plus 5/2 ds. Whatever that turns out to be, that's our answer. All right, so we now know what we need to compute. Now we have to compute it. Okay, well, let's tackle a couple things here. Let's start by handling the ds. What is ds going to be? Well, now we're a two-dimensional integral, so that's going to be the square root of x prime squared plus y prime squared dt, which is going to be the square root of, let's see, x prime. So the derivative of x will be 6t. So 6t squared. Then what's this? Well, the derivative of y, well, that'll be a 6 square root of 3. And then I'll have a t squared, and I'm going to square that, dt. Now, notice that in both cases, they have a 6t in common. So there's a 6t here, there's a 6t, and then here I'll be left with a square root of 3t. Since they both have 6t in common, I can factor that out. So I can think of this as 6t quantity squared times 1 plus, and here I'll be left with square root of 3 squared, 3, and t, there's a single t left, and I square that. 3t squared dt. And of course, the 6t comes out. So 6t square root of 1 plus 3t squared dt. Now, unfortunately, there's no hope to factor the square root of 1 plus 3t squared. It's just not going to happen. So, but we'll keep going. Now, there is hope, though, because one can't help but notice taking the derivative of 3t squared gives us 6t dt. So it really looks set up to be just right for a substitution. But we have some other stuff here we're going to have to think about. All right, so let's see where this takes us. Okay, so here we go. This will become the integral. We update, our time bounds are going to be 0 to 1. We update what we're integrating, so we're going to integrate 1/2 times x. So that's going to be 1/2 times 3t squared. So that's 3/2 t squared plus 5/2. Okay, ds is going to become 6t square root 1 plus 3t squared dt. Now we need a plan, a good plan. Not just any plan, a good plan. But we kind of alluded to it. If we think of the inside here, let's call that u, then the 6t will become our du, really our 6t dt. Say, well, that's fantastic, but we have other stuff here. Well, how do we handle that? Well, notice if we have 3t squared plus 1 is u, then we can say that 3t squared is really u subtract 1. And I have a 3t squared here. So what can this become? This can become 1/2 u subtract 1 plus 5/2. Or, if we clean it up a little bit, a half u, and then we have minus a half plus 5/2. That'll be 4/2, also known as 2. So, if we do this substitution, what do we end up with? Well, we're going to end up with the integral. We update our bounds. So 0 and 1 were our old bounds. So we plug in t equals 0, and we're going to end up with 1. Plug in t equals 1, we're going to end up with 3 plus 1, which is 4. And then we're going to have 1/2 u plus 2. That's the part here. Then we're going to have square root of u, or u to the 1/2, and then the 6t dt becomes du. So this becomes the integral from 1 to 4 of 1/2 u to the 3/2 plus 2 u to the 1/2 du. Now we're making great progress. We're ready to integrate. So we're going to get 1/2. We add 1 to our exponent. That'll be 5/2 multiplied by the reciprocal, 2/5. Plus 2, add 1 to the exponent. That'll be 3/2 multiplied by the reciprocal. That'll be 2/3. So when we simplify, we're going to get 1/5 u to the 5/2 plus 4/3 u to the 3/2. Now we have to evaluate from 1 to 4. Now 4 turns out to be a very nice number since square roots are involved. Square root of 4 is 2, and 2 to the 5th would be 32. So 32/5. Then we're going to have another square root of 4, which is 2, but now cubed, which is 8, times 4. Well, 8 times 4 is 32/3. And we're going to subtract, plug in 1. Now, plug in 1 is easy because we just grab the coefficients, 1/5 and 4/3. Now, common denominator will be 15, 5 times 3. So we're going to get 96, because I multiply by 3, over 15, plus, big one, that'll be 160 divided by 15, because you multiply 32 times 5, well 30 times 5 is 150, then you have another 10. Subtract 3 over 15, and subtract 20 over 15. So what do we get? Well, 96 plus 160, that would be 256. If I subtract 20, that would be 236, and if I subtract 3, that would be 233. Is that right? Yeah, 233 divided by 15. Cubic feet, because that's the answer. That's the area, and the amount of area is the number of cubic feet we need. All right, well, not the cleanest answer, but that's okay. The process works. And this one is a little bit more interesting, of course, because, you know, we have the DS is not so clean. You work it out. But the key thing is you can work it out. It is possible. These problems are all possible. You just have to be patient, remember how things work, and take your time. Take your time. There's no bonus points for being done quick, but there's lots of points for being done correctly. All right, keep practicing.